So today we're going to talk about lipid chemistry for the next 3 lectures. The end is getting so close. You must all be so excited. So today we're going to talk about lipids, and specifically we're going to talk about one aspect of lipids really, because we don't have time to go into all the different types of lipids, but today we're going to talk about the major class, which is triacylglycerols. The other major components when we talk about lipids are things like cholesterol, phospholipids, sphingolipids, ceramides. So these are all the apolar lipids or the polar lipids. These typically are used more as minor ingredients, things like surfactants in the food industry, and in some cases don't really play a major role. Things like sphingolipids don't play a major role in the food industry, but are very important for messaging, as molecules for messaging. So today again we're going to specifically focus on the triacylglycerols, which are what we typically talk about when we talk about fats and oils. So when we talk about lipids, depending on the state they're in, whether or not they're a liquid, in that case a liquid oil, or if they're a solid, we term them a fat. Now what's going to be the characteristics which defines a liquid oil versus a solid fat? What molecular feature is going to drive it to remain in its unsaturated state? Oh, I just gave it away. Oh man, sorry. So one of the aspects that determine whether or not a fat is an oil or a solid is the melting temperature of that fat. When we talk about low melting temperature triglycerides, we talk about unsaturated, so your EPA, DHA, oleic acid, linoleic acid, linolenic acid. What else will determine whether or not, yes? So the presence of unsaturation is one. Yep. Cis and trans. So the geometric configuration of that double bond. Are the hydrogens on the same side of that carbon backbone, or do they go across? The length of the chain. So right now what we're starting to see is that we're starting to see a lot of medium chain triglycerides being incorporated into food products because they are heat stable. They don't oxidize readily because there's no double bonds, but they're short enough that they remain in the liquid state. So things like palm oil are very good frying oils where we are going to continually temperature abuse that oil. So when we talk about oils, typically they are liquid at room temperature, whereas fats are solid at room temperature. Now, when we talk about triacylglycerols, although we often talk about the fatty acids, so the actual, if there's a double bond present or the chain length of that fatty acid, every triacylglycerol is made up of 3 fatty acids esterified onto a single glycerol molecule. Now, glycerol, so glycerol has no chiral carbons, right? There's no chiral carbon in glycerol. Now, once we esterify fatty acids onto that glycerol backbone, SN1, so we have SN1, SN2, SN3. Once we esterify a fatty acid onto one of those glycerol positions, SN1 and SN3 become different, right? So because of the esterification of fatty acids, this carbon, as long as SN1 and 3 are different fatty acids, if they're different fatty acids, then SN2 becomes chiral. Now that only works if SN1 and 3 are different. Now, when we talk about the melting point or the physical properties of triacylglycerols, it's dependent not only on whether or not there's fatty acids that are unsaturated or saturated, whether they're cis or trans, as well as whether or not they're long or short chain. But it also depends on what 3 fatty acids are there. So if it has 2 saturated versus an unsaturated, compared to another triacylglycerol that has 3 saturated, they're going to have different melting properties. Now, when those fatty acids esterify onto onto glycerol, there's the release of 3 water molecules. So breaking that bond is dependent on the presence of water, right? So this is really important. So When we put on, or when we esterify on a fatty acid, there's my aliphatic chain. Water leaves that reaction when they form that covalent bond. So to break that covalent bond, we need the presence of water. Now this is really, really important, especially when we talk about frying oils. Can anyone tell me why this matters when we talk about frying of oils? Who here eats at fast food chains? McDonald's, Burger King, anywhere they deep fry French fries. Now, for those that have their hands up, when you go to that McDonald's, Burger King, you don't see it as much in Canada as you did in the US. You would see it all the time in the US. But sometimes when you go to a establishment that's using oil as a frying medium, what do you notice when you come up to that building? Even before you go in? It smells like grease. What else is there? Sometimes, not always. The presence of smoke, right? Now, whether or not there's smoke coming out of their heat exchanger or their vents is dependent on how old that oil is. So if you have a batch of oil and you're continually heating it up to 250, 300 degrees Celsius so you can undergo frying, you put your potatoes in that oil, all of a sudden that frying is a drying mechanism. It's going to pull that water out of the system. As it's pulling that water out of the system, it allows for the hydrolysis of free fatty acids. And if you hydrolyze a free fatty acid in a high temperature environment, it becomes volatile. It can move into the gaseous state, right? So this is a good indicator. If you see like a gray smoke coming out of a fast food establishment, chances are their oil hasn't been changed regularly and you're undergoing hydrolysis. That means you're getting so much water accumulating in that oil or that frying medium that hydrolysis is happening. Now, hydrolysis in itself isn't anything that's dangerous, right? We hydrolyze fats all the time to digest them. We cleave position 1, we cleave position 3, we absorb the 2 fatty acids, we absorb the 2 monoglyceride, and then we reassimilate them into chylomicrons. So from a nutrition perspective, the fact that it's undergone hydrolysis isn't really a big deal. And we're going to talk a lot about hydrolysis in about 2 days. But where it's really important is if you undergo a lot of hydrolysis and you lower the boiling point of those oils, that means fatty acids are going to be coming to the gaseous state. That means we have a much lower autoignition temperature or flash point. What does this mean? If you use a cooking oil over and over and over again, it's more likely to undergo combustion. You're more likely to have a grease fire. This is dependent on how much water is going into your system, which is able to facilitate the hydrolysis of triglycerides into fatty acids. So we'll come back to that. So when we talk about the melting profile, or the melting temperature, or the rheological properties, how hard that fat is, it's dependent on the distribution of fatty acids on glycerol, as well as the different species of triacylglycerols that are present. So if you have a whole bunch of fats that are all saturated in all 3 positions versus a whole bunch of fats that are all liquid in the 3 positions, they're going to behave very differently than if you have a saturated fat at, let's say, positions 1 and 2 and an unsaturated at position 3. And we'll talk about that distribution in a lot of depth. But first we've got to talk about the physical attributes of the individual fatty acids themselves first. And why we have to do that is because, again, triacylglycerols are made up of the 3 fatty acids, and the physical properties are dependent on the fatty acids that are present. So the 3 attributes we're going to talk about are aliphatic chain length. So how long, how many carbons does that fatty acid have? Whether or not it's saturated or unsaturated. So if it's unsaturated, the presence of a pi double bond, and that presence of that double bond changes its reactivity. We're also going to talk about the difference between a cis isomer and a trans isomer. We all know trans fats are bad for us, but trans fats have really, really excellent physical properties. So if you want to make a cocoa butter substitute, or a shortening or a lard type substitute using plant oils, trans unsaturated fats provide very desirable physical properties. Again, from a nutritional perspective, they're very, very detrimental. And we'll talk about that. So we're going to talk about chain length, saturated versus unsaturated, and then the distribution between cis and trans. So, remember when we talk about aliphatic chains and that presence of those CH2 groups, we're in that sp3 hybridization, so just like methane, we get that even distribution of electrons around that molecule, and because of that, we get only temporary dipoles for interaction. So the non-covalent interactions that hold triacylglycerols together are dependent on the van der Waals interactions, or those temporary dipole moments. Now, those temporary dipole moments are dependent on temperature, right? So like hydrogen bonding, as you heat the temperature up, the interactions, the strength of those van der Waals interactions deplete once you get above 40 degrees Celsius. That's why fats melt. So when we talk about nomenclature of fatty acids, there's three primary ways we can name. The most common is the common name, which really is just straight memorization. So C4 is butyric, C6 is capric, C8 is caprylic. You notice there's no odd-numbered fatty acids up there. In our food supply, up until recently, we really didn't have a lot of vegetable oils or animal-based oils that had odd-number fatty acids. They don't play a significant role. One of the reasons is because of the mechanism for elongations of fatty acids, we add 2 carbons at a time. The exception to this now is the introduction of algyl oils. So algyl oils are becoming very, very popular as a substitute unsaturated liquid oil. But because of that, we see now the presence of some odd-numbered fatty acids. But really, our food supply is made up of only even-numbered fatty acids. And they're classified based on their chain length. So the short chain fatty acids are anything less than 10 carbons. So the abbreviation here, the first number indicates the number of carbons. So in this case, we have 4 carbons. The colon representing the number here, this number represents the presence of double bonds. So 0 means we have none, 1 means we have 1 double bond, 2 means we have 2 double bonds, so on and so forth. The downfall to that abbreviation system is it doesn't indicate where that double bond is. And why is this important? This becomes really important from a nutritional aspect when we talk about omega-3s versus omega-6s. Because position tells us a lot about the nutritional profile or the nutritional benefits of that fat. So the abbreviation system doesn't account for, doesn't indicate where those double bonds are present. The IUPAC name really isn't commonly used anymore. We typically now see butyric, caprylic, caproic, but it's important to be able to recognize the defining features of the IUPAC name. So again, you should know, where's the little laser pointer? I don't know where it is. Is it up here? I was using it a second ago. Oh, it's just not showing up. So bute represents 4 carbons, hex 6, oct 8, dec 10, and then enoic acid is indicative of the presence of the carboxylic acid group. Once we put it onto a triacylglycerol, we drop that enoic, the OIC, because that carboxylic acid group is now esterified into an ether group. So short chain fatty acids, very characteristic of flavor profiles, especially when they've undergone lipolysis and that free fatty acid is no longer esterified onto the glycerol backbone. Anyone know a process in the food industry where we try to promote the lipolysis of short chain free fatty acids? Cheese ripening, blue cheese, camembert, brie. These all rely on undergoing lipolysis reactions so you get that milky characteristic flavor. So in butyric acid, we typically see that really in the food industry only in dairy products. Caproic, caprylic, and capric are very indicative of goat's milk. Lauric and musteric as well as palmitic, are the main fats found in palm oil derivatives. So in the palm oils, we typically see the medium and long chain fatty acids. And there's a lot of debate right now going on whether or not medium saturatids behave like long chain saturatids in the body. And again, this is really still an area that's actively being debated right now. And then when we talk about the long chain saturates, we're talking palmitic, so C16, C18, which is stearic, and C20, which is arachidic. Stearic acid, very, very common in butter, as well as animal meats. So again, these are our saturates. As the aliphatic chain length increases, the number of carbons which can undergo van der Waals interactions increases. So as the chain length increases, the melting point of that fat increases. So when we talk about our fats, things like cocoa butter, lard, tallow, fully hydrogenated canola oil, we're talking about long chain saturated fats which are giving the structure. So up till about C14, C16, that's when we start to see very unique solid-like properties in things like cocoa butter, lard, and other solid fats. Now, when we move into the unsaturated fatty acids, we replace the alkane with alkene. So alkanoic acid becomes alkenoic acid. Now, again, we typically don't rely very much on IUPAC naming in the food industry, and instead we rely on the common naming. Where it gets tricky and where the food industry, the chemists and physicists differ from nutritionists is how we name our unsaturated oils. From an IUPAC standpoint, you always start from the largest, most oxidized group, right? So in the naming of fatty acids, we start from the COOHN because that's the largest functional group, the most oxidized functional group that is on that carbon backbone. For some reason, nutritionists start at the other end, at the methyl end. So when you talk about IUPAC naming, in this case, in this molecule here, we start from the carbon closest to the most oxidized position. So this is position 1. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 16:1. Again, doesn't indicate where that double bond is. If we use the IUPAC name, it is 9-octadecanoic acid, or more commonly known, this is 18:1, oleic acid. If we start from the omega end, so an omega fatty acid, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it happens that it works out to be equal both ways. But again, omega starts from the methyl end. IUPAC naming starts from the carboxylic acid end. So if you're talking to a chemist and say your first double bond is at position 9, you could talk to a nutritionist and they would say, no, it's at position 3. We're talking different mechanisms of naming. So the chemist style, again, starts at the most oxidized group, position 1. The nutritionist starts at the methyl end. And I don't know why we don't have a ubiquitous naming system. But you can see here, if we name over, we have position 9. And again, if we move over, we have position 9 for linoleic acid. This breaks apart when we start to talk about omega-3s and omega-6s. Omega starts from the methyl end of that molecule, okay? If we talk about IUPAC naming, it starts from the carboxylic acid end. Now, we have two different phenomena that can happen here now. We can have the change in chain length and the degree of unsaturation change. The more double bonds you put into an unsaturated oil, the lower the melting temperature is. So 18,3 linoleic acid has a lower melting temperature than linoleic acid, 18:1. So the more double bonds that are present, the lower the melting temperature of that fat. So when we talk about formulating a food or a product, something like ice cream, we really have to be careful in the fatty acid distribution of that fat to understand or to be able to predict how hard that fat is going to be at that specific temperature. So we tailor the amount of saturated versus unsaturated fat to play a very specific role in how they structure fats. Now, when we talk about biologically relevant fats and oils, so anything that comes from a plant, and 99% of triglycerides and fatty acids that come from animals are in the cis configuration. Meaning, those two carbons are on the same side of that aliphatic backbone. So they're on the same side of that double bond. Why is this important? The biggest reason this is important is it impedes the ability of that fat to crystallize. Now, why is that? We talked a little bit about polymorphism, and we're going to talk about it a lot today. So that's a triacylglyceride. So if you imagine that this is a triacylglyceride, the seat of this molecule, or this chair, would be the glycerol backbone. And coming off of that, the back and the two legs, so imagine there's only two legs coming off, so this and this are joined. So we have one straight chain fatty acid, one straight chain fatty acid, another straight chain fatty acid coming off. Because of that, I can very easily pack those chairs. That is crystallization. When those triglycerides pack in close proximity to one another, the van der Waals interactions between adjacent methyl groups in the aliphatic chain will form very weak aliphatic bonds, but if there's 18 or 20 of them, they become significant. Now, if you imagine, I'm not going to do it, but if I bend the back of this chair and put a big kink into it, the next time I bring a chair in, so again, imagine this is bent over, I'm not going to be able to bring that next triacylglycerol and pack in effectively. It's going to be much, much more difficult for that molecule to come into and establish a fat crystal network. Does that make sense? So again, imagine you've got some saturated fats. If they're all saturated, they line up very, very easily. And they can form a crystal structure at much lower temperatures. Now, if we introduce a cis double bond into that fatty acid and mix it with some straight chain, you can see how much more difficult that is to pack those fatty acids. So every time there's a kink in one of those fatty acid chains, you can think of it as an impedance to those molecules being able to align with each other and form a good cohesive crystal network. This is why they tend to be liquids at room temperature. Now, if we change that geometric isomer from cis to trans, now trans is not typically found in the environment, in the food supply, I should say, with the exception of one food source that has significant trans, which we'll talk about in a second. But now what we see is when we go to that trans configuration, they now have the ability to stack in a very similar fashion that we observed in the fully saturated. So in the 70s, when hydrogenation was becoming really popular, the idea of it was, well, we're preserving that double bond. So biologically, we thought this would behave in a similar fashion to oleic acid. The downfall to this, clearly, is that it plays a really weird role in regulating the amount of cholesterol in our body, which we're going to talk about. So these are cardio-deteriorative. They have a negative impact on cardiovascular health. These, the cis, have a protective effect on cardiovascular health. So just this change in isomerization, or the cis-trans geometry, is enough to change how our body recognizes and metabolizes and utilizes that fat. From a physical chemistry standpoint, this is very good. So I can take liquid canola oil, I can partially hydrogenate it, forming a lot of trans fats, which then behave like saturated fats. So I can take vegetable oil and make it into a fat that resembles an animal fat or a plastic fat that's solid-like at room temperature. So I can make inexpensive cocoa butter equivalents, or I can make inexpensive replacements for butter. Why is this important? Well, if you're selling a bag of cookies for $1, you don't want to put in an expensive ingredient like an animal fat. You want to use really inexpensive canola oil that's been processed, partially hydrogenated, to get that solid-like fat characteristic. So the difference between a cis and a trans isomer changes how those molecules can pack. Therefore, it changes the physical properties of that liquid oil to solid fat, as well as the biological considerations of those fats and oils. So, does anyone know where trans fats are naturally found in our food supply? Milk of ruminants. So very low in the meat, quite high in the milk. So we have two predominant trans fats in our food supply. The first is transvicinic acid. The other is conjugated linolenic acid, CLA. Both of these are trans fats. Both of these are products of the dairy industry. There's a lot of really interesting and, again, contrasting literature on whether or not those trans fats are as detrimental as transaladic. Transaladic acid is the fatty acid that's predominantly found from the hydrogenation of oil seeds, of things like canola, rapeseed, sunflower. So it's interesting that they play such an important role just based on the difference in geometry, whether or not they have a beneficial health effect or not. So if we take our glycerol molecule, and every glycerol molecule is esterified to 3 different fatty acids. The properties of that triacylglycerol are dependent on what 3 fatty acids are present. And again, so if we have a fat that has 2 saturated and 1 unsaturated, depending on where that unsaturated fat is, if it's at position 1, 2, or 3, will actually change the physical properties. Now, the thing that's really challenging about the fats and oils industry is we can fairly easily characterize what the population of fatty acids is within a product. So I can say it's 20% unsaturated, and then I can break that unsaturated down pretty easily to say that it's 5% oleic, 10% linoleic, and 5% linolenic. So getting the fatty acids present in a food is very easy. Getting the distribution of triacylglycerols is extremely hard. So if you imagine, just from a random probability, we have 3 different positions, and any one fat is made up of n number of fatty acids. So if we have 1 fatty acid, we have 1 possible molecule that can be produced, right? If we have 3 different fatty acids, we have 3 to the exponent 3 different possible combinations of that fat. Now, if we have 20 different fatty acids, that means we have 3 to the 20 combinations of triacylglycerols, if it's completely random, right? So if the odds of any one fatty acid is random, meaning it's going to be as likely to be at position 1 as it is 2 as it is 3, this holds true. So this is what we call even or widest distribution of fatty acids. This never occurs in nature. So this doesn't really happen, meaning nature selects for those fatty acids to preferentially be located at different positions. So, as an example, when we talk about most plant-based oils, they typically have their unsaturated oil located at the SN2 position. And this is really interesting, and we don't really know why this happens, but the SN2 position typically has the highest bioaccessibility. Why would that be? Can anyone think of why that might be? Why would SN2 preferentially be absorbed over SN1 and SN3? Not stronger bonds. We've already talked about it in great depth. We're just switching the application. Why would SN, yes? So it's, no, not because it's chiral. What does lipase cleave off? SN1 and SN3. It's the 2-monoglyceride that moves across the epithelial cell before it's reassembled into a triglyceride and incorporated into a chylomicron. So that SN2 is preferentially absorbed. So if SN3 is cleaved off, and let's say it's stearic acid. So that's 18 carbons. I'm not going to draw out the 18 carbons. I have a carboxylic acid group. This, in an acidic environment, is protonated. Nothing really exciting happens. When it moves into the intestinal phase, what's going to happen to that COOH? pH is now around 6.5 to 7. It's going to become deprotonated. If it becomes deprotonated, it can form a salt with different ions or different minerals. Specifically, and the one that causes the most problems, is calcium. So when you have a lot of saturated fat at position, long chain saturated fat, things like stearic acid, and they get cleaved off, and if you have a lot of calcium, they form calcium soaps, and that calcium and fat transitions through your body, and you lose out on the bioaccessible fractions. So you actually diminish the bioaccessibility of both calcium and fat in an environment where your SN3 position, SN1 and SN3 position are long-chain saturated fatty acids. Now, what's interesting is SN2 is very typical to have an unsaturated based oil. So we typically see what's called restricted random, meaning the biochemistry of that plant or animal preferentially places double bond or unsaturated fatty acids at position SN2. So when we talk about the distribution of cocoa butter, if we look here, we can see that at SN2, so here's position 1, 2, and 3. We can see that oleic acid, and I always get this mixed up, linolenic and linoleic. If we look at the two of these, this is the vast majority of the unsaturated oil. So the majority of the unsaturated oil is located at SN2. If we look at SN1 and SN3, you can see that those are predominantly saturated fatty acids. So what this means in the case of cocoa butter, and cocoa butter is extremely unique, every triglyceride has 2 saturated fats and 1 unsaturated fat. Now, the length of those fatty acids at position SN1 and 3 are a little bit different because we have fairly high proportions of both stearic and palmitic acid. So the melting temperatures difference for a difference in one methyl group is not, or sorry, 2 methyl groups is not all that significant. It's a degree or 2. So what we see in cocoa butter is triglycerides that are remarkably similar. So what does that mean? Cocoa butter has a very unique property compared to most fats and oils. So if we look at the melting temperature, So here we have solid. So how much solid is present? And here we have temperature. Now, if it's completely random, so if those fatty acids are completely randomly placed on that glycerol backbone, we're going to have the widest possible melting profile, right? Because you could have, in theory, a triglyceride that's completely unsaturated, that SN1, 2, and 3 are all unsaturated, so it's got a low melting temperature. And likewise, you could have another triglyceride that's all saturated. And then you would have every combination in between. So in a completely random distribution of fatty acids, we have a melting profile that looks like that. So this is a random distribution of fatty acids. Does that make sense? So the more chemical diversity you have, the more different melting temperatures you have. This means that as you heat up, your solid fat content, or whether or not that triglyceride is going to be in the liquid state or the solid state, is going to decrease as temperature goes up, and those small populations or proportions of molecules begin to melt as we move up. Now, when we restrict the position of those fatty acids to different loci on glycerol, we get a much narrower melting distribution. So now again, remember in the case of cocoa butter that the vast majority of triacylglycerides have an SN1 and 3 position that are either palmitic or stearic, so almost the same melting temperature, and at position 2 we have an unsaturated oil. So the vast majority of triacylglycerols are saturated, unsaturated, saturated. And there's not a big distribution in the chain length within cocoa butter. So what we see in the case of cocoa butter is a very, very sharp melting point. And does anyone know what the melting temperature of cocoa butter is? What's the temperature of the human body? 37 degrees Celsius. Cocoa butter melts perfectly at 37 degrees Celsius. On Thursday, we're going to talk a lot about chocolate, and you'll see that if you put a piece of chocolate in your mouth, what happens to it? It melts. What happens, and I don't recommend you do it, if you put a piece of lard in your mouth? It's like holding a piece of plastic. It doesn't melt. You don't get that lubricity. You don't get that coating, because lard behaves far more like this, and we'll talk about why it does, than cocoa butter. Now this melting pattern is necessary for good quality chocolate. So irrespective of where you buy your cocoa butter from, if it's Nigeria or Costa Rica, the chemical composition of those are very, very similar. In that SN1, SN3 are C16 or C18. Position 2 typically is 18.1 or 18.2. So to make fats that behave like cocoa butter is extraordinarily difficult to do, because the chemistry to place specific fatty acids at specific points on glycerol is very, very difficult. This, from a chemicals perspective, is easy to do. We can make and substitute all kinds of fats that have very broad melting ranges. That's easy. Very specific, very sharp melting transitions are extremely difficult when we talk about naturally occurring fats. Again, because that distribution is not only dependent on where they are on the glycerol backbone, but it's also dependent on the species, the length of that fatty acid, and the degree of unsaturation. So cocoa butter is very, very unique in how it has 2 saturated and 1 unsaturated, again giving that very sharp melting profile, making it very difficult to make cocoa substitutes. And you'll be trying one on Thursday, a confectionery-based fat that has no cocoa butter. Now, not only does the position of that fatty acid on the glycerol backbone play an important role in determining the physiochemical properties of that fat, it also plays an extremely important role in the bioaccessibility. SN2 position fatty acids are far more bioaccessible than fats that have, than fatty acids at position SN1 and SN3. Why? Because once they've been cleaved off at position 1 and 3, when they move into the ileum, duodenum, and duodenum, pH goes up, they become deprotonated, they can then form ionic bonds with other constituents. If they form an ionic bond with a salt, it forms an insoluble soap. That insoluble soap is not absorbed. It passes through the body. So, when we design fats to be used specifically in preterm infants or in infant formulas, we typically try to modify that fatty acid that's at position 2 to be whatever the most beneficial fat is. So if we're fortifying with something like fish oil or something, I don't know, whatever we're adding, EPA, DHA, we want those fatty acids that are biologically relevant to be at the SN2 position to ensure that the bioaccessibility of that goes up. Make sense? Irrespective of the plant source, almost always is that SN2 position an unsaturated oil. So it has preference. Milk fat has a preference to place the short chain butyric either at SN1 or SN3. So all fats undergo the process of restricted random placement of fatty acids on that glycerol. So we tend to get sharper melting profiles or sharper crystallization profiles of naturally occurring fats. Yes?
Aren't the free fatty acids easier to assimilate within the body? So
Are
free fatty acids easier to assimilate in the body?
Well, so once the free fatty acid crosses the epithelial cell, it's then reassimilated within that epithelial cell. So that SN2 monoglyceride seems to be taken up more efficiently than the fatty acids. Again, because fatty acids can form soaps, can form complexes with other molecules, and then won't be absorbed. But once it's absorbed, there's no preference of reassimilation. That's gone at that point. Does that make sense? Okay. So this is my expertise. This is what I'm good at. So when we talk about structuring with fats and oils, it's extremely complex. So we've already talked about the chemical complexity of a triacylglycerol. So when we talk about the fatty acid distribution, we have a handful of molecules, 20 or so different molecules that we can pull from, right? C4 to C20, and then we've got the 3,18 unsaturated, 18,1, 18,2, 18,3, and then we've got EPA and DHA. There's a few others, but those make up the vast majority of fatty acids that are in the diet right now. Now, when we talk about the crystalline network, it's determined not only by the fatty acid composition, but also the triacylglycerol composition. So imagine again, we have 20 different fatty acids esterified onto glycerol in many different ways. So that triacylglycerol is a mixture of many, many different triacylglycerols. So in the case of cocoa butter, we have 3 primary fatty acids. So if we go back to that slide, if we look at palmitic, stearic, oleic, that makes up 90% of the fatty acids that are present in that triacylglycerol, right? Now, if we do the distributions, again making sure that we recognize that SN2 is predominantly oleic, even in a completely random environment, we can have S, S, S. So if it's completely random, P, 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 O, 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 S, O, P, S, O, O, S, S, O, S, P, O. There's going to be 27 different combinations that we can have. That's not that many. If we completely randomize that, we'll have 27. This doesn't really exist, or it exists in such small amounts that it's completely irrelevant. This doesn't exist. This doesn't exist. So what we end up with is SOP, POS, POP, and SOP. We have 4 different triacylglycerols. That's it. Now, those 4 triglycerides melt at remarkably similar temperatures because SOP and POS, again, although they're different because of the chiral carbon at position 2, melting point is almost identical. If we take away 2 carbons from here, the melting temperature of this will be about 2 degrees different than the melting point of this. Again, not relevant when we talk about the melting profile. Yeah? Yeah, SOS. There we go. So again, we have so few chemical species that melting point is very, very sharp. Now, if we imagine something like canola oil or rapeseed oil or any other oil, we typically have a lot more chemical variability within our fatty acids. We have musteric, we have palmitic, we have stearic, we have oleic, we have linoleic, we have linolenic. So all of a sudden now, we introduce a lot more chemical complexity and we broaden that melting point. Now, fats, just like sugar solutions, are never completely crystalline. Meaning, we have our triglyceride molecules. So here's our triglyceride molecule. Those triglyceride molecules pack into highly ordered structures. Those highly ordered structures are called lamella. So right here, with 2 chairs, you have a lamella. The lamella is a perfectly arranged crystal structure. So these 2 molecules make up 1 lamella. If I put another chair in there, we now have 3 lamella. And those lamella stack into crystals. Now, within these little tiny crystals, like splinters, you can see, if you look really carefully, banding. Those are the lamella. There's a couple, 20 to a couple hundred stacked lamella that are perfectly crystalline. Think of a salt crystal. Now, when those begin to form these spherulites, these are the things that determine how hard that fat is, how spreadable that fat is, if that fat is grainy or it's really smooth consistency, is determined by the size and shape of these spherulites. Now, those spherulites are made up of nanocrystals. Those nanocrystals are made up of a lamella, and the lamella are made up of triglycerides. Now, depending on how you process that fat, you can change the structure of the lamella. This is what we term a change in polymorphism. We've already talked about once where polymorphism is important with the association of bloom in chocolate, the form 5 beta polymorph going to the form 6 polymorph. So we can change how these crystals are stacked together, right? So you can imagine we have 1 polymorph here. We have a second polymorph here, and the lamella associated with these 2 crystals are different, right? So you can imagine again that the back of that chair is made up of 18 carbons, and the legs of these chairs are made up of 18 carbons. So for every carbon, we have a very small van der Waals interaction. So based on these 2, there's all different physical properties that differ based on the lamellar structure. First, the density of these 2 molecules, or these 2 crystals, is going to be different. You should be able to see that just by looking at the chairs. The melting point is also going to differ. Here, you can see that we have 18 carbons interacting, and then the legs of the chairs also interact. So we have 18 carbons, 18 carbons, 18 carbons, all undergoing weak van der Waals interactions. This dense crystal is going to have a higher melting point than this less dense crystal. You only have 18 carbons interacting. These don't form van der Waals interactions in this lamellar structure. Does that make sense? So the way on a molecular level that these triacylglycerols pack into that lamella structure define the physical properties of that system. This is dependent on how you process your fat. So when you talk about good quality chocolate, you have to force the molecules to pack in a specific arrangement so they melt at the temperature of your mouth. If they don't, they become waxy. They become plastic. They get that very diffuse surface. They aren't glossy anymore. They turn that gray appearance. This is because of the changes in polymorphism associated with how we crystallize that fat. Cocoa butter A, cocoa butter A. We have just cooled it differently, which has changed how that molecule can pack. So we change polymorphism not by the chemical composition of that fat, but instead we change polymorphism based on the processing of that fat. So if you don't cool cocoa butter properly or temper it, you don't get the desirable polymorph. So you have to create a process that forces the appropriate polymorphism. Now, once you get those lamella stacked into domains, and those domains into nanoplatelets, and then those nanoplatelets into spherulites, every different level of structure is dependent on how you process that fat. So you can change the structure of a chocolate bar depending on how fast you cool it and whether or not you're mixing or stirring that cocoa butter as it's crystallizing. So shear or mass transfer and temperature, heat transfer, both play a significant role in determining the final physical properties of any fat or any solid-based lipid. And we'll talk about that in a lot of depth. What you have to remember is the structure of that fat is dependent on chemical composition, but now we've introduced another factor, which is its processing. How do we cool it? How do we mix it? What other additives do we add? We literally, so Alex Marangoni is a Tier 1 Canada Research Chair, as well as a Royal Society Fellow? Royal Society of Canada Fellow. So he has done all of the pioneering work on understanding how structure is influenced not only by processing, but also by chemical composition. Why is this important? Well, 20 years ago when we started making milk chocolate, we used to get these crystal structures in milk chocolate sometimes that weren't desirable. You would see accelerated bloom, you would see softening of that fat. A lot of his early work in his career was spent understanding how that hierarchy of structure influences the macroscopic sensory properties, the melting point. How can you engineer a fat to behave like another fat? Why do you want to do that? Again, when you're talking about making a cheap, inexpensive processed food, you want to use low-cost ingredients. If you can understand the structures that build that final physical network, you can then begin to look for less expensive fats to have very unique properties that are typical only for very expensive fats. Things like cocoa butter and butter. Those fats we want to emulate, right? Margarine is a great example. Margarine is designed to behave like butter. Does it? Not really. It's not horrible, but it's not great. Cocoa butter, again, much more difficult to find cocoa butter equivalents that behave and melt like fat. Now, when we go from a liquid to a solid, we initially have to get the formation of an interface, right? So those molecules that are in the liquid state have to arrange themselves into a crystalline structure. Once they've arranged themselves into a crystalline structure, that's a new phase. They have new physical properties. So the interface that's associated with that has a free energy associated with it. To overcome that, we term nucleation. So nucleation are the number of sites where crystal growth can take place. The more nuclei you have, the smaller those crystals are. You have more surfaces, so you have less growth. So if every one of you represents a triglyceride, if I get 10 of you to stand up and saying, you 10 are my nuclei, everyone else move to one of those nuclei. The size of that aggregate is going to be bigger than if I say 20 of you stand up. Now all of you go and hold hands with those 20 people. We're going to get much smaller crystalli because we have more of them. So crystal size is inversely proportionate to nucleation number. So the number of nuclei always is inversely proportionate to the size of the crystals we have. So if you want to have more triglycerides, more solid crystals that are smaller, why would you want them smaller? You don't want to detect them in the palate. If they become too big, that fat becomes really, really grainy. Again, take a piece of lard, put it in your mouth. You will detect the graininess of lard. We can modify that by chemically modifying the species that are present or by changing the processing conditions. So nucleation and crystal growth is highly dependent on the rate in which we cool and the presence or absence of shear. So it's dependent on heat and mass transfer. The faster we cool, the more nuclei we get. The slower we cool, the less nuclei we get. So when we develop unit operations designed to crystallize fat, we need to get high heat transfer coefficients. We need to cool that fat down quickly. Now, as we're cooling that fat down quickly and it's crystallizing, it's going from a liquid oil to a solid fat. We need instrumentation that's designed specifically to not only handle a liquid, but also to handle a solid fat. So we have to introduce a baffle or a shearing mechanism, to almost like a screw, that will push that solid fat through. So any unit operation that we design for the crystallization of fats and oils, we have to consider both the heat and mass transfer of that system. Now here's where lipid chemistry, especially the physical chemistry of lipids, becomes very complicated. Is we have our triglyceride molecules. This depends on our source of our fat, if it's from canola, if it's from animal, if it's from rapeseed, if it's from whatever. It's also dependent on any chemical processes that we do to the fat. So there's a few processes, hydrogenation, interesterification, which we'll talk about, that modify the position of those fatty acids or the presence and absence of unsaturates. So the glycerol molecules are modified prior to crystallization. Once we undergo crystallization, we only modify from this point upwards. So we can modify the lamella structure, right? We can modify the polymorphism, which we'll talk about. We can modify the size of those lamella, which means we modify the size of those independent little crystals that are perfect. We modify how those crystals stick together and form crystallites, so those branched, so you can see there's liquid oil all entrained within the spherulate. So this is a mixture of solid and liquid. Out here is just liquid. So depending on how we crystallize it, how fast we crystallize it, if we input shear, we can change the size of the clusters. If we change the size of the clusters, we change that distribution, how big they are. If we change how big and how many they are, we change the sensory properties of that fat. So when we talk about high quality fat, not only do we have to be cognizant of what triglycerides are present, but we also have to be very, very knowledgeable on the thermal conditions that that system has been placed under. How fast did we cool it to? What temperature did we cool it to? Did we introduce any mass transfer coefficients that need to be talked about? Things like shear. Did that play a role? So when we talk about the final physical properties of a fat, again, it's not only dependent on the source of that fat or the triacylglycerol molecules that are present, but it also depends on heat and mass transfer, how fast it was cooled, and if it was sheared or if it was unsheared during that crystallization process. Now, just like we talked about in water, when it crystallizes, we go through this first phase, that's supersaturation. Supersaturation is the difference between the melting temperature and the crystallization temperature. Water, pure water, melts at what temperature? 0 degrees Celsius. What temperature does pure water crystallize at? That's dependent on how fast we cool it. So typically it'll crystallize, if we put it in our freezer at home, anywhere around -5 degrees Celsius. But if I take a droplet of water and throw it into a bath of liquid nitrogen, I may not see crystals until -30 degrees Celsius. The crystallization temperature is dependent on the rate in which we cool that fat. The faster we cool it, the more supersaturation we get, the further below the melting temperature we get. So the crystallization temperature always occurs at a temperature below the melting temperature. And again, we need to do this because we need to overcome the energy associated with the formation of a new interface between that crystalline phase and that liquid phase. So supersaturation is the time temperature combination below the melting temperature. So it's dependent on how fast you cool that fat down. If you cool that fat or water, doesn't matter, really slowly, it's going to have time to reorganize and crystallize somewhere near the melting temperature. You put it in your freezer at home, it's going to crystallize somewhere around -5 degrees Celsius. So again, that supersaturation then would be -5 degrees Celsius. If we can rapidly cool it, we can drive that crystallization temperature down. Now, the supersaturation is the driving force for nucleation. So the further below the melting temperature you go, the more nuclei you get. So if you crystallize your bottle of water at 5 degrees Celsius, and you take it out, and remember you bang it on the counter and that crystal grows, you can literally watch that crystal growing. That's how large that nuclei is. That's how few nuclei you have, is that you can actually witness crystal growth. If my supersaturation is very high, meaning my melting temperature and my crystallization temperature are very different, that's a larger driving force for crystallization. That means larger driving force for crystallization, more nucleation. If we get more nucleation, we have less subsequent crystal growth. More nuclei, smaller crystals. So nucleation and crystallization are always contrasting each other. Because if molecules are being used to form nuclei, and we have more nuclei present, we have more surfaces for those fats to crystallize onto. So more nucleation means smaller crystals. Smaller crystals typically means better sensory properties. So you don't want that graininess. You don't want to be able to detect the size of those fat crystals. And once they're above about 5 microns, you can begin to detect them in the palate. So if those crystals have grown too large, that fat becomes sandy. So supersaturation is the driving force for nucleation. Now, nucleation goes from completely disordered so there's an isotropic melt. No order. Isotropic means that every dimension is completely unordered. Now, we can change the amount of order that's present in this system. So there is one dimension, right? They're lined up this way. No order this way, no order this way. So that's a one-dimensional crystal. Now we have order in 2 axes. This is a 2-dimensional crystal. Whenever it's less than 3 dimensions, we call them liquid crystals. Really important when we talk about the formation of plasma TVs. We talk about liquid crystals. Now, if I had more chairs, and I began to stack them upwards, we would now have a triglyceride crystal, which has 1, 2, 3 degrees of order. So a 3-dimensional crystal is what we typically talk about in the food industry when we talk about fats and oils. Now, liquid crystals, or less than 3 dimensions, can happen. Things like lecithin are really good at forming 1- and 2-dimensional crystals. Other polar lipids and fatty acids are very, very good at forming liquid crystals. Liquid crystals don't play a major role in the food industry. Very important in pharmaceutical, cosmetic science, but not that relevant when we talk about structuring of foods. We're almost always talking about 3-dimensional crystals when we talk about fats and oils in foods. So there's 2 main types of nucleation. The first is homogeneous nucleation. This is when all of the nuclei appear at once. Heterogeneous nucleation occurs as nuclei appear during time. So you start with 1 nuclei, and then 2 nuclei, and then 3 nuclei, and then eventually thousands of nuclei. Whereas homogeneous goes from 0 to 1,000, literally within milliseconds. So homogeneous nucleation, all of the nuclei appear at once. These typically are large degrees of undercooling. Undercooling is just another term that is used to describe supersaturation. Again, heterogeneous nucleation, nuclei appear more slowly and typically occur at lower degrees of undercooling or lower supersaturation. Now, the size of the crystals is inversely proportionate to the degree of supersaturation. So, as your supersaturation goes up, so we'll go supersaturation, and number of nuclei goes up, crystal size goes down. Always inversely proportionate to one another. So whatever's happening with nucleation, if we have lots of nuclei, they're small. If we have few nuclei, they're large. Does that make sense? Okay. So, the ability of a triglyceride to form a nuclei is dependent in how fast we cool it down. So that's the heat transfer. And it's also dependent on the characteristics of that liquid oil. How viscous is that oil? So that triglyceride, which is randomly distributed in 3D space, has to be able to diffuse from the liquid to that nuclei. This is dependent on mass transfer. Are we mixing it? Are we shearing it? What's the viscosity of the continuous phase? Is there natural convection? Is there forced convection? Is there no convection at all? That plays a role in determining the size, shape, porosity of that crystal network. So you can imagine, if you have very few nuclei, you're not going to be able to entrain liquid oil very well. So imagine it like a building blocks. You're building a house, you want lots of walls that go up, and anything that's trapped in that room becomes impeded the closer those triglycerides get together. The closer they get together is dependent on how many there are and their size. So it's always very difficult to try to understand or predict ahead of time whether or not that 3D network that forms is going to be sufficient to be a self-standing, let's say, gel or colloidal network. Is it not going to be able to be detected? Is that fat going to cinerease oil? Meaning, is that oil going to drain from that network? This is all dependent on how we structure, so it's dependent on the mass and heat transfer of how we crystallize that fat. This becomes more and more complicated as we introduce more and more ingredients, because we add interfaces which can actually cause nucleation. So here is 2 different fats. Doesn't matter what the fat is, but under different rates of cooling, you can see here that here we would have a very, very high supersaturation. A very high supersaturation, you can see each of these little splinters is a crystal. So just in this little region, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crystals. This is a single crystal growing out. So this massive crystal is very different than these small broken up crystals. This you could detect in your palate. This you wouldn't be able to detect in your palate. So difference in polymorphism as well, which we'll talk about in a little bit. But again, when we talk about nucleation rate, it's always inversely proportionate to crystal growth rate. The smaller the crystals, the more nucleation, the greater supersaturation, the greater the supersaturation, the greater the degree of undercooling. High degrees of undercooling in the food industry, very difficult to do, right? The rate in which you cool down or cool a system with is dependent on how fast you can remove heat. This is dependent on the geometry of the processing unit operation as well as the temperature of the cooling medium we use. Typically in the food industry, we don't use anything other than refrigerated ammonium, so we can only get down to about minus 15 to minus 20 when we talk about driving forces for inexpensive crystallization processes. You can use things like liquid nitrogen in the case of dipping dots, but a small container of dipping dots is several dollars, whereas a carton of ice cream is several dollars. So you're buying maybe a tenth of that ice cream for the same price because you're paying for that process and that storage. So again, the physical properties of that fat are dependent on the size, the shape of those crystals, and those size and shape of the crystals are dependent on the triglyceride molecules that are present, as well as the processing conditions. Now, when we talk about processing conditions, one of the most important attributes we talk about is polymorphism. And there's two different aspects of polymorphism. There's the unit cell and the subcell. The unit cell is the length of the triglyceride. So here, the unit cell would be 1.5 times the length of that triglyceride, right? So 1, there's half, there's another half. That makes sense? Here, it would be the length of the triglyceride. That's the unit cell. So that unit cell, when we talk about polymorphism, isn't that important. So we have L, we have 1.5 L, and I'm terrible at, and then 2L. The subcell is how the methylene groups pack. So if we look at it from the M point here, it's how do these tips arrange in three-dimensional space. So if we had a whole bunch of pencils, and I was holding those pencils, and I took 4 pencils, imagine the different configurations I could put those 4 pencils in. I could make like a square, I could make like a hexagon, or I could make kind of a shifted square, like a polynomial. So if we look at the methylene groups, that's what this is. So here we're looking at the unit cell or the long spacing, which is dependent on the triglyceride leg. The subcell is dependent on how those legs are arranged in three-dimensional space. So we have hexagonal, orthorhombic, triclinic are the 3 main polymorphic structures we see in fats and oils. The hexagonal or alpha is the least dense, and as we move across here to beta prime and beta, this is the most dense. So least dense to most dense. This affects melting temperature, hardness, how that fat behaves over a temperature range. So the unit cell is the triglyceride length. Subcell is the end view of the methylene groups on the fatty acids. When we talk about polymorphism, we talk about the subcell. The subcell is what's relevant when we talk about melting temperature. Okay, this is a really good place to stop. On Thursday, we're going to pick up here, and we're actually going to look at tempering of cocoa butter and how to make quality chocolate.